Recording.
Okay. Well, it's a pleasure for me to present now Professor Manuel del Pino of University of Bath. Manuel is a great mathematician. Fortunately, he's a friend of me, he's a colleague, and we are a student together in the same university long time ago. And Manuel, maybe all the people known, he have a lot of publication and honors. And now it's a great pleasure to present him. Manuel talk today about a problem titled Delaunay type compact equilibria in liquid drop model. Please, Professor Manuel, you can start.
Okay. First of all, thanks Mauricio for the nice introduction. With Mauricio, just maybe I will give a figure. We know each other. We have been friends actually for about 40 years, if I'm not wrong. Huh? Anyway, I thank you for the invitation. It's an honor for me to participate of this great workshop. And okay, so the topic of my talk today is a topic with a relatively classical problem in calculus of variations that I will describe, which is called the liquid drop model. Okay, the liquid drop model was introduced by in nuclear physics by Gamow in 1928, and it was essentially intended to model the energy of a nucleus, thinking of the nucleus as a region in space, okay, where coexist protons and neutrons, okay, and which are distributed with about constant density, and so that the volume of the region omega is proportional to the total number of nucleons. Very large, of course. And essentially in this model, the region, okay, the correct region or the region selected by nature should be critical, okay, hopefully stable, okay, stable critical point for this energy. So omega is the unknown, omega is the variable, okay? So what we want to find are critical points of this energy, however, subject to the volume, okay? So for a given volume which we prescribe, we want to find, using some Lagrange multiplier rule, okay, critical points of this, okay? Okay, so then in this energy, the perimeter represents the area of the boundary, okay? And this energy combines this perimeter term that corresponds to surface tension, that intends to model surface tension, and because, I mean, at the boundary, okay, for the particles located at the boundary, and another term that corresponds to repulsive Colombian interactions. Okay, so that's the idea of this second guy. Okay, where you see it is involved the Coulomb potential, the Coulomb repulsion. Okay, so what we are interested in is in stationary regions omega under the volume constraint of volume of omega equal to m. Okay, where m is a given positive constant. So a basic example of stationary regions are ground states with a given mass m. And what are these ground states? They correspond to minimizers, okay, of, in case that they exist, of the energy, subject to the volume constraint. Okay, so that's the simplest type of stationary point or critical point that we can imagine. There is these solutions of this constraint minimization problem. Well, it turns out that the following is known. It is known that ground states do exist, provided that the mass is sufficiently small, while they do not exist if the mass is large. Okay, this is a fact. This is known. I will try to explain it intuitively in a moment. So the stationary problem amounts to finding regions omega with vanishing first variation of perimeter with respect to normal perturbations of the boundary that preserve the volume M. Okay, give me a second. I will open this file again. I'm not sure why this red line appears. Anyway, I think you can see correctly, right? Yeah, I will just leave it. Yeah. Okay. The stationary problem corresponds then to finding these regions omega with vanishing first variation of perimeters with respect to normal perturbations of the boundary that preserve the volume M. Vanishing first variation of the energy, okay, rather than perimeter. Remember, you have two terms, the perimeter for surface tension and the repulsive Colombian interactions. Okay. In the smooth case, finding this corresponds to finding a region omega with volume M, okay, such that for some constant, Lagrange multiplier lambda, we have this relation satisfied, which is mean curvature for the boundary, evaluated at points at the boundary, plus this Coulomb potential term, okay? And what we want is that the sum of this and this is a constant, okay? And this constant corresponds to the Lagrange multiplier corresponding to the volume constraint. Oops. Yeah, I don't understand why these red lines appear. Anyway, Bohr and Wheeler, Niels Bohr, okay, introduce this specific problem to compute the minimal energy required for nuclear fission. Okay, here it is the energy written again. And it turns out, I mean, and this is an important observation, that balls with volume M are always solutions of this problem, okay? Why is that? Well, because the mean curvature is constant, right? And if you use the invariance and the rotations of this quantity when integrated on a ball, okay, you will quickly see that this is also constant, okay? So we actually have this relation for points at the boundary, points Y at the boundary. Okay? And what's the reason is because balls are both critical for the mean curvature term and for the Coulombian term. These are, however, critical points of different characteristic. First of all, let me remind you the classical isoperimetric inequality, okay? The classical isoperimetric inequality for the perimeter definition, the area of the boundary, defined in the sense of de Giorgi, yeah? The isoperimetric inequality states that the minimizers of the perimeter of regions with volume M is actually attained by balls of volume M. Okay, this is well known, and this is what is called the isoperimetric inequality. And of course, since this is a critical point of the perimeter, then we will have mean curvature constant. Mean curvature is the derivative of the perimeter, okay? Somehow, the first variation. And Ries actually, long ago, 1930, actually proved that balls not minimize, but maximize the Coulombian term interaction, okay, with volume M. So somehow the repulsive interactions are maximized in a ball, while the surface tension is minimized. This is the trade-off. This is the combination of the two. Okay, so we also have this, and therefore we have the validity of this identity, as I mentioned before. Anyway, but since the two terms, as I said, describe opposite effects because minimizer and maximizer. The problem of finding non-trivial critical points, say all the critical points that are not just balls, okay, is a delicate one. Let me mention something that is not really in the slide, but I think is important to emphasize, is that the critical points of perimeter, namely constant Minkowski surfaces, okay, that are embedded and compact, are always balls, and this is true not just in 3 dimensions, but in any dimension. Yeah. Okay. Let me observe the following. So just to give you some intuition of why of what is going on here. We can scale out the mass, first of all. If I let omega be this specific number, the m to power 1/3 times E, then we will have that this region E will have volume 1. So, and now defining the number alpha through this relation, what we immediately get is that the perimeter, okay, of alpha is alpha squared times the perimeter of E. Yeah. And the Coulombian interaction is transformed through a simple change of variables in this way. Yeah. And here is the relationship between the energy of omega and the corresponding energy for E. Okay. The energy of omega times this constant is actually equal to the perimeter of E plus the number m and times the Coulombian interaction at E. Yeah. And this suggests the following. Observe. Even though these are opposite effects, however, if m is small, for instance, this guy is weaker, right? And we know that there are minimizers of perimeters and with area 1, with volume 1. And in fact, these minimizers are balls. So it is plausible that we will actually have minimizers if m is small. And this is indeed true. Yeah. Not only that, if the mass is sufficiently small, it is also known that these minimizers are balls, okay, which is not obvious either. While if m is large, the second guy will be dominant, and then it is also understandable that in that case, we should have no global minimizers. Okay, let me consider now the following number. The following number, this number m star, okay, which is a critical mass. Yeah. Let me tell you what this critical mass represents. This is precisely the value of the mass for which the energy of one ball and that with mass m star and that of 2 balls of mass half, okay, of m star located at infinite distance so that the repulsion becomes negligible, okay? If you consider that situation, then it turns out that the 2 energies coincide. So 2 times the energy of balls with half the volume is actually equal to the energy of the single ball with volume m star. Okay, this is the ball included here. So this is a special connection, and this special connection actually tells us something else. It tells us that the ball, a single ball, cannot be a minimizer. In fact, it's not completely obvious from here, but it turns out that not only these 2 guys become equal, but actually, if you consider masses slightly bigger, this guy to the right will be lower, okay? And that means that at least the ball cannot be a global minimizer. If there is a global minimizer, it's not a ball, okay? So this is the subtlety of this number m star. There is a conjecture that was probably formulated by physicists much before, but this was due to Choksi and Pelletier in 2011. What they propose is that the following situation holds, which is more or less logical, right? If m is less than m star, then the infimum is attained precisely when omega is a ball. So the balls are minimizers according to this conjecture whenever m is less than m star. Yeah. While if M is bigger than M star, case in which the ball is not a minimizer, it is actually additionally claimed that the infimum is not attained at all, so that there is no global minimizer. Yeah. So this is the situation. This conjecture has been partly proved, but its full statement is still open. Okay. Let me make a little summary of what is known or what has been proven about this problem. So first of all, what is known is the existence of a number M1, small number M1, yeah, such that whenever the mass is less than M1, balls are minimized. So balls are minimizers for small m, for small mass. And we have different works that are actually simultaneous in time approximately by these people, by these authors, establishing that fact. Now, on the other hand, it is also proven, it is also known that for m less than or equal than m star, there exists a minimizer. Please observe that the existence of a minimizer, that statement does not involve the fact that minimizers are balls. So that part of the conjecture is open. On the other hand, it is also known that for large m, if m is bigger than 8, okay, 8 is another special number which is much bigger than m star. This m star, remember, was something like 3.5, okay? But if m is bigger than this specific number 8, it turns out that no minimizers exist. And this was proven by Frank, Kilip, and Nam in 2016. Now, the fact of using other potentials other than the Coulombian potential, but Riesz potentials, okay? And or changing the parameter by fractional parameter versions or inhomogeneous versions. This has been analyzed by several authors, in particular the people that I mentioned here, the works that I mentioned here. So in summary, for this small number M1, from M1 to 0, balls minimize the energy. There is no minimizer. There exists a minimizer between M1 and M star, but actually from 0 to M star, there is a minimizer. However, from N star and to 8, balls are not minimizers. And in fact, beyond 8, there is no minimizer at all. And there is yet another number that was known already from Bohr and Wheeler, okay? Actually, they realized that at 10, something special happens. There is a bifurcation phenomenon, okay? The ball doesn't get unified, doesn't correspond to a ball anymore, but some type of splitting start going on here. At mass 10, balls are no longer stable. They are not stable critical points. So they are stable below 10, if you wish, second derivative positive definite in that sense. They are not global minimizers, but they are local minimizers. And beyond 10, they are not simply not stable. So the question that we would like to address here, yeah, is the following. Are there solutions to the original problem, to the problem of constrained critical points, with large mass, which are not necessarily minimizers? So finding such solutions is an interesting, important problem. Say, if the mass is bigger, what type of stationary configurations can we find? Other than balls. Balls are always critical points, but of course we would like to see more interesting things, right? Okay, people have studied this issue both in the rigorous way, okay, and the numerical way, okay. Frank in 2019 actually analyzed the local bifurcation branch that happens at the mass equal to 10. Remember, at 10, the ball ceases to be stable when we reach mass 10. This picture, okay, is is a numerical picture from these authors. in a very recent paper, in which what they detect is that for mass bigger than 10, this psi star, imagine, is 10, okay? And chi is mass. For them, this a different notation. This picture is taken from their paper. So for mass bigger, we have the ball, and we have this other object, oblate-like, which is perhaps a local minimizer, yeah, which has this form, while to the left, the balls are minimizers, and there is something like a mountain pass here, yeah, like a Morse index 1 solution going to the left, yeah, and this is the prolate. And this has been analyzed numerically, even continuing the branch to what's going on. Let me tell you what they detect. Please don't ask me details about how they carry out the numerics, but this is what they see. The Boran-Wheeler bifurcation branch, so which is the branch at mass equal to 10. Say mass equal to 10 says here. Say here is when we see the ball, okay? That's 1. What we would say 1. 1 would correspond to mass 10. And when the mass starts going to the left, going to 0, towards 0, then you start seeing these shapes, and at some point the shape loses convexity and starts becoming, look at what it becomes. It becomes, when the mass is very small, 2 balls. Okay, so there should be a mountain pass that behave like this. This is not known rigorously. Yeah? Let me insist on that. It is, however, plausible that a solution like this exists. While if you go to the right, this shape becomes this funny thing. Okay, it also loses convexity. However, you start creating something that is torus-like, yeah, toroidal type surfaces. So this is the situation, or the numerical presumptions. Yeah? Concerning a rigorous result in 2011, Ren and Wei, yeah, established the following: established that if you consider a sufficiently large mass, then there exists an axially symmetric torus-like solution, so exactly axially symmetric, that looks like this, yeah? So this is not exact torus, okay? But however, it is axially symmetric. So they were able to find a torus-like solution with a section that is not exact circle, yeah? But it's close to be a circle. And they also estimated the large radius and the small radius for the torus to be these numbers for mass sufficiently large, yeah? So R is like M modified by this logarithmic term, and the little r goes to 0, and goes to 0 slowly with them, yeah, like this. That solution is unstable. However, it is important, and it is what seems to be observed numerically. More details about the stability of this thing you can find in this survey, very nice survey about the problem, published in 2017 in Notices AMS by these authors. Anyway, let me remind you something that is also very classical, okay? Constant mean curvature surfaces. Constant mean curvature surfaces, lots of them are known, okay? And the simplest ones in 3D are axially symmetric ones, okay, that are not compact, however, are periodic and have this approximate shape, a periodic shape that looks like this, okay? These guys depend on a parameter we call A, which is some inner radius, the small radius, the next size, okay, that oscillates between 0 and 1/2. And when the next size is 1/2, the torus, this guy becomes a cylinder, yeah? So a cylinder is a solution. It's a constant mean curvature thing, right? And when the parameter starts getting smaller, you see a shape like this, like, this curly thing. And And when the parameter reaches certain limit, the next size is 0. When the next size is 0, what you see is an infinite array of spheres, okay? Like indicated here. And actually, there are also surfaces that continue to exist when this parameter gets negative, but these surfaces are not embedded. They have self-intersections, like in this picture. Yeah. So this is what is known about the Delaunay surfaces, the axially symmetric things. So here is another nicer picture for a Delaunay surface, or for a piece of the Delaunay surface. So it's a sort of sphere-like, then connected with another sphere through a neck. Okay, the neck turns out to be a catenoid, asymptotically. Okay, then. Let me consider a parametrization of this sigma, of this surface sigma, which since it is rotationally symmetric, it can be written like this. So, okay, x bar is the first two coordinates, and x3 is the coordinate of the axis. This is what this means. Yeah, so the absolute value of x bar, okay, is a function of x3. That's the situation. Okay, so this function f of x3 is periodic of period t sub a, where t sub a is some specific period for which you can compute easily the limiting values. Okay. In addition, I can make this decomposition. The sigma, yeah, the full surface, can be decomposed as the union of these basic cells. And why? Because this guy is periodic, right? The surface is periodic, so you can actually decompose it in this way. Let me consider the truncated version of it at the height n, okay? Which is the union of the sigma case of n of these cells from 0 to n. And I call that surface sigma n. And I consider also another surface that I will call sigma n h, which is nothing but the same surface, however perturbed by a certain normal perturbation, which I will also assume periodic, okay? And even in the variable x1, and this is convenient for me for a reason that I will tell you in a moment. And this function is also periodic of the same period as the one of the sigma case. So, okay. And also I assume evenness in x3. Okay, so what is this nice picture? This is the type of solution that I would like to construct. Okay, it's not obvious that something like this exists, but I will show you that I will try to convince you that that something like this exists. What I do is I take a Delaunay surface and I twist it. Okay, I twist it to construct something of this form. Of course, if I do this, I need to have a very specific relation between the radius, yeah, of this thing, the distance to the axis of the Delaunay, and the period, right? So this is not for free. Precisely what you need is this: 2 pi times that distance capital R, right, is n times the period. So it should behave like it should be like this. Yeah, that's the connection between n little n and capital R. So capital N large is capital R large. Now I do the following. In order to describe the corresponding normally perturbed thing H, I consider sigma n H, the sigma n perturbed by the normal thing H, to the point R E2, and I rotate it in the plane x2, x3. This is what I do. Yeah. Now, if I want to be explicit, I can use cylindrical coordinates, okay? And in cylindrical coordinates, that surface that I call sigma nh is transformed into another one that I call the same way, but with a tilde, which is the image through this map x, which are cylindrical coordinates of the original truncated thing. And this is a Delaunay color, okay? With n cells, okay? This is the idea. I call the three-dimensional region enclosed by this sigma tilde I call it correspondingly omega NH tilde, yeah, like I show here, okay? The volume of this guy is approximately n times the volume of the single cell, so if n is large, yeah? Because the curvature of this guy is very small in reality, right? It's a very large radius, very large disk. And the volume of the cells actually can be precisely estimated by these. These are the limiting values for A going to 1/2 and for A going to 0. Yeah. A, remember, is the next size. Okay, so here is our main result. This is joint work with Mónica Musso from Bath and with Andrés Zúñiga from Universidad de O'Higgins in Chile. Okay. And you can find the preprint of this in arXiv. And the statement, our statement is the following: given a mass M sufficiently large, there exists a smooth domain that I call omega with volume little m that has this form. It's simply a certain scaling of this omega tilde and h, yeah? And this scaling occurs with a suitably small gamma and a normal perturbation h, such that small perturbation h, normal perturbation h, such that for some constant you have this. So what I claim is the existence of a solution that looks like a collar, okay, for all large masses. Yeah, this is the statement. I will try to give you an idea of why this of our strategy to prove this result. To do that, let me first show you the derivation of the problem P. Yeah, and for that I need to compute the first variation of this guy. And what we have then is this, the energy is this, and along normal domain perturbations, then I have sigma h given by this guy, yeah? So what I find is that this is the Lagrange multiplier rule, okay? What I need is the derivative of the energy needs to be lambda times the derivative of the volume, right? So because it's the volume, the constraint is volume constant. Then lambda is the Lagrange multiplier, and we evaluate it when the normal perturbation is 0. If you do this computation, actually, you realize that the following happens. First, that the first variation of the Coulombian term becomes this, yeah? And this is also well known, actually. The area or perimeter of the boundary, the area of sigma h is the area of sigma, the limiting thing, plus this quantity here that involves mean curvature. Yeah. And this is how we end up after some small computation to the validity of this relation. Yeah. We will have a solution to our original problem if and only if we have this identity holding. Okay. So concerning the derivation of the mean curvature term, there is a lot of computations we can do and find very explicit things involving the second fundamental form, also with explicit forms. And we use these computations very carefully. To derive what, you may ask? Okay, I will tell you in a moment what we are trying to derive. If I make the scaling of the surface omega with this parameter, arbitrary parameter but small, gamma to negative 1/3, what I see is this relation. So this is the relation that I want to get, okay? Now let me consider the following integral. I will tell you the role of this integral in a second. This complicated guy, where f is what? F is the profile, okay, of the Delaunay, yeah? And this quantity plays a role, okay? Something that I can tell you, this quantity is positive when A is small, so small next size, but also if if the next size is close to 1/2 to the cylinder, and however, it's enough that it's bigger to 1/4, is also positive. The truth is that we believe that this quantity is positive all the way. However, we honestly didn't prove it, okay? And however, we do believe that. Probably could be done using some good numerical approach, but we were not able to find it. So the main step in our proof corresponds to the following. For the proof of the theorem, given a small value of some a between 0 and 1/2 fixed, and such that integral I sub a is positive, then for all sufficiently large n, there exists a number gamma, which is of this order, 1/log n, and a function h, a perturbation h, with size also 1/log, so it's small, yeah, such that this happens, such that we have this, such that this identity holds. This is the main step in the proof. Actually, once this is proven, the full result for arbitrary large mass can also be found. Anyway, so the proof or the construction of this perturbation h, little h, is done using some fixed point argument. And the fixed point argument is actually based on expansions for this quantity, for the energy of the limiting surface, yeah. And after if you are smart enough in the computations, then you get the following expansions, yeah, for the mean curvature to begin with. The mean curvature of this sigma nh is this guy. So this is not tilde and this is with tilde. This is the twisted thing. This is not twisted guy. And you get this term. You get this funny term here. And when you expand the mean curvature, you get the limiting mean curvature sigma n plus the Jacobi operator at h. Yeah, this is the linearized of the linearization of the mean curvature. Yeah, you get and then you get quadratic terms. And the Jacobi operator is this guy here. This is Laplace-Beltrami term. This is the norm of the second fundamental form squared. And the quadratic term can depend also on first and second derivatives of h. So, then concerning this, the proof is just straightforward computations, however, a little bit lengthy. Yeah, I will skip that. And the Coulombian non-local operator you can also expand in a good way. And in fact, you find that the guy with the tilde can be expanded with the tilde unperturbed by h can be expanded by the guy unperturbed plus a term that is gamma log n times the mean value of h. So what do we do? What we do in order to solve the full problem is to invert or to formulate it as a fixed point problem involving the Jacobi operator. Yeah, the kernel of the Jacobi operator is known. This is the non-degeneracy of the Delaunay surface. This is another classical fact. And the equation that we want to solve is actually something of this form, yeah, at the end. So it is very convenient actually to do the perturbations in such a way that the mean value is 0, which actually is consistent with not taking other volume, letting the volume be 0, be constant, yeah? So this is the type of perturbations that we wanna do. And if you do the computation, what we prove is that we can find gamma such that the equation holds, okay? And how is this gamma found at main order? Using test functions, the right test functions. In order to preserve this in particular. And what we end up finding, okay, is the existence of this number gamma, yeah, of the right number gamma, after testing this against some Jacobi field, okay, an element of the right element of the kernel. And eventually what we end up finding is that our full problem is solved if we solve an equation like this, yeah, where this is some inverse constraint projected inverse for the problem. And then gamma is found making E gamma integral of E gamma times nu2, the second component of the normal vector, which is a Jacobi field, equal to 0. So, and in fact, this is why we needed this number IA be positive, because we need gamma to be positive, right? And to get a gamma positive satisfying this, you need this number positive, because you want this guy be 0. Yeah. Anyway, so I don't have really have time to do more details. But at the end, you use a simple continuity argument, continuation argument, to prove that you can actually see solutions of this form for any sufficiently large mass. Okay. Anyway, so perhaps let me conclude in 1 minute just with the following. With Rupert Frank, we are actually working, and Monica Musso, we are actually working in the following. You remember what I showed you at the beginning of the bifurcation branch when the mass goes to 0, that we could find a mountain pass solutions that look like this. This can be proven actually with the same type of method. And this is something we have discovered recently, it's not written yet. And but hope it will come out soon. So thank you very much for your attention.
Thank you very much, Manuel. Now I want to ask if there is some questions of the audition. Please. Now is the audio is open for the question. You can ask. Manuel, I have a question, a simple question. You consider the number m, the mass m or the volume m is a mathematician number for you, but when I think in mass or volume, there is some physical units that there is a relation between the real mass, for example, for atomic particles, when you call the mass m, your number m is related with that, with the physical mass or
you mean that like these critical numbers, m star and so on? Huh?
Mm-hmm.
I have received that question.
Mm-hmm.
My co-author Zúñiga has that picture more clear because that goes really inside physics, right? So it's this is of course after normalizations, after all kind of normalizations, and this number is essentially a-dimensional. But indeed, in the true world, right? They correspond to some atomic numbers of some type. Absolutely.
Okay. Okay. Thank you. Other questions? No. Okay, we thank again the Professor Manuel del Pino for this nice presentation with a lot of nice picture and equation. Thank you very much, Professor Manuel.
Thank you very much for the invitation. Thank you, Mauricio.